Have you ever stopped to think about the hidden physics behind, I don't know, a ball flying through the air or a car speeding down the highway? It turns out everything that moves, and I mean everything, is governed by two fundamental ideas, force and motion. So let's dive in and see how the world around us really works.
But first, let's kick things off with a little puzzle. Imagine this. You just ran a full 400-meter lap around a track. You're exhausted, but you finish right back at the starting line. So here's the question. What is your displacement? Keep that word in your head, because the answer is pretty surprising.
All right. The key to solving that little puzzle is understanding that in physics, we actually measure a journey in two totally different ways. We've got to separate the winding path you actually took from the straight line between where you started and where you ended.
First up, we have distance. Now, this is the one we're all used to, right? It's the total ground you covered, every single step you took. A great way to think about it is like the odometer in your car. It just keeps on adding up no matter how many turns you make.
This picture shows it perfectly. To get from the house to the lake, you have to follow that long, winding road. That entire route, every single curve and bend, adds up to your total distance traveled. It's the journey itself.
But then there's this other thing called displacement. And displacement is totally different. It couldn't care less about the scenic route you took. It's just a direct, straight-line measurement from your starting point to your ending point. You know, the as the crow flies path. It's simply the shortest possible line between point A and point B.
Okay, so now that we've got those two definitions, distance and displacement, let's circle back to our runner on the track and finally solve that puzzle.
So here it is, the big reveal. Your distance is 400 meters. No doubt about it, because you ran every single inch of that track. But since you ended up in the exact same spot where you started, the straight line distance between your start and end point is, well, it's nothing. Your displacement is 0. This little table really makes it clear. In a 100-meter sprint, you're running in a straight line, so your distance and your displacement are exactly the same, 100 meters. But for that 400-meter race on a curved track, the distance is 400 meters while the displacement is a big fat 0. Pretty wild, right?
And listen, this isn't just some neat trivia for track and field fans. This distinction is absolutely crucial. It's how your phone's GPS gets you home. It's how pilots navigate their planes. It's all about knowing the difference between the path you took versus the most direct route. Okay, so now that we have a better handle on how to describe motion, let's ask the next obvious question. Why do things move in the first place? Well, the answer is actually incredibly simple. It all comes down to force.
And that's pretty much it. At its very core, any interaction that causes something to move, speed up, slow down, or change direction comes down to a force, just a simple push or a pull.
The crazy thing is, we are using forces constantly, all day, every day. Pushing a grocery cart, opening a door, hitting a tennis ball, lifting a bag, even just turning on a faucet, it's all just the physics of pushes and pulls in action.
So, if a force is really just a simple push or a pull, what can it actually do? Well, it turns out this one simple action has 5 really powerful effects on the world around us. So here are the big 5 things a force can do. It can get something moving or stop it. It can change how fast something's going. It can change its direction. It can make it spin, and it can even change its shape. Let's take a quick look at each one. First up, a force can get things moving. An object at rest is going to stay at rest until a force acts on it. Just think about the incredible muscular force this tiger needs to use to launch itself from a dead stop into a full-on sprint. That's a force starting motion.
Number 2, a force can change the speed of something that's already moving. When you step on the gas pedal, the engine applies more force to make the car go faster. And when you hit the brakes, you're just applying a force in the opposite direction to slow it right down.
Third effect, a force can change direction. A cricket ball is flying in one direction toward the batsman, but then, bam, a sharp force from the bat instantly sends it flying in a completely new direction. It's the same idea when you turn the handlebars on your bike.
All right, number 4. Forces can make things rotate or spin. When you turn a steering wheel, you're not really just pushing it forward. You're applying a force in a way that causes it to pivot around a center point. And that, my friends, is rotation.
And finally, number 5, a force can actually change an object's shape. When you squeeze a stress ball or bend a paperclip, you are applying enough force to physically deform the object itself, whether that's temporary or permanent.
So if forces are doing all this stuff, how in the world do we measure them?
Well, we use a pretty simple tool called a Newton's spring balance. The more a force is able to stretch the spring inside, the greater the force. Simple as that. And the standard official unit we use to measure force is called the Newton, which we just write with a capital N. So in the world of physics, you wouldn't just say you pushed a box. You'd say you pushed it with a force of, say, 50 newtons.
So let's bring it all home. From a simple walk to the store to the most complex machine you can imagine, everything is really governed by these two connected ideas: how we describe motion and what forces are causing it.
You know, you can really boil it all down to this. Motion is just something changing its position over time. And a force? Well, that's just the push or the pull that makes that change happen. Which leaves us with one final, fascinating thought. We now know that you need a force to change an object's direction. A satellite is constantly changing its direction as it orbits the Earth. So, what's the invisible force that's constantly pulling on it, keeping it locked in that orbit without any engine? Now that's a great question for another explain.